We'll see to the good guy. Thanks a lot for this invitation and a nice introduction. Yeah. So I find myself a little bit between a rock and a hard place because I was supposed to talk on blackboards, but I actually don't do. I'm not quite sure what should come out of this lecture, so that was not entirely clear to me. So what I'll try to do is, if you look at QCD at colliders, there's lots of concepts which, in a very bizarre way, look very different, and then they don't look very different, but come together, and at some point they look different again. So it's a relatively rich field with a rich phenomenology, with a rich theory behind, and with a lot of very different approaches to sort out specific problems. So I try to explain the concept in such a way that if you're interested, you have a vague feeling what it is, and yeah, you have to go to literature. So the outline is, and yeah, please feel free to interrupt me at any moment. I'm not religious about finishing anything. We stop where we stop, right? So I'll very briefly introduce the QCD Lagrangian. It's mainly just a warm-up thing to make sure that we're on the same page. I'm kind of quietly confident that we managed to do that today, and kind of go into a few more fun things. So one of the things I will try to explain to you is what the objects in QCD actually are and why they're relevant objects. And so that's in this basic concepts. Then we do a little bit about fixed order, and I will just again try to summarize something that Kieran did in much more detail. And if you get bored, you just let me know and we skip stuff because maybe it's boring. And then we do something that Kieran didn't do, which is which goes under the name of resummation or QCD at all orders, and we see how far we can push it. And then depending on time or not time, we may even go to some non-perturbative aspects, which is where we don't know much really quantitatively, and we rely very much on models. And I would explain a couple of the models. Okay, so let us start with the Lagrangian, and we take it as granted, right? But it was far from being completely obvious why people would arrive at something like QCD. And I don't know. I think historically it's kind of amusing to realize that when quarks were introduced, no one really believed they were real. They were just a mnemonic device. So in the 50s, people found new particles, mesons and baryons. I wouldn't say on a weekly basis, but quite frequently, and looked like a completely irrational zoo of stuff that no one really understood. And at some point, people introduced quarks, and only later people realized then that these guys actually exist. So, so what we know is they're strongly interacting particles. They form the bound states, and we know that they're spin 1/2 particles from scattering experiments, from the angular distribution of scattered particles, and from some rules. So it's pretty much fixed. We know mesons consist of a quark-antiquark pair. Baryons consist of 3 quarks, and in order to get charges of plus minus, electrical charges of plus minus 2, plus minus 1, and 0, you have to do something. And the way to do it is to have triple charges like plus 2/3 and minus 1/3, and then you're good. Now the first thing that people fell over was the realization that there's a particle called the delta plus plus, which is a doubly charged baryon. And for that to work, you needed 3 U quarks, and they would all have to be in a spin up state because the delta is a spin 3/2 particle, so you have 3 spins that have to align. And then you run out of quantum numbers because it's fermions, spin 1/2. So and it's an S wave. And then you have the Pauli exclusion principle, and you can't have 2 states, 2 particles in the same state. And that's not optimal, right? So people were forced to invent something, and they just invented color. And they called this charge color because that was the time when color television was invented. And therefore the colors were red, green, and blue. Makes complete sense, right? It's the primary colors of a television. So that's how it works. And like in the television, you know, if you add red and green and blue, you get white. That is very nice. If you do it with your watercolors, you get a muggy brown. Not so nice. So don't do watercolors. Very simple rule. So red, green, blue together gives white, so no charge, or you do red and an anti-red. And this is how baryons and mesons work out. Now, I'm not going to talk about these funny tetra-quark states or so. Okay. No idea how they fit here. Now, the true success of this thing was, so people invented this quark model and everyone was sort of baffled. But, and no one really believed that there's anything really in it. But then this object here, omega minus, got predicted with the right mass. And people found it. So this was one of the first particles that got predicted and was found. And this sets a precedent for how particle physics ever since worked. Theorists make predictions of particles or structures based on symmetry principles or theories, and they hope that they pass the litmus test of being found. So we can trace back to some degree the logic of predicted discoveries back to the late 1950s when omega minus was predicted and found. Okay, so how do we put this into a field theoretical framework? So we write down the Lagrangian, and we already said the quarks come in 3 colors. Now, if you want to have a theory that has 3 charges, the simplest thing you can do is an SU3. So why not try an SU3? And turns out it works. So in SU3 you have 8 generators, and those are the 8 gluons. They relate to the Gell-Mann matrices, which look a little bit like the Pauli matrix, just in 3 dimensions. So these TIJs here, I have them on one of the further slides. They look pretty much like the Pauli matrix, just in 3 by 3. I'm not going to discuss the gauge fixing. I think Kieran did that. And then you arrive at your Lagrangian, and I think the one thing that is important to note is that in contrast to QED, the gauge kinetic term has this extra self-interaction term. So if you put the G mu nu together, you get triple and quadruple gluon vertices. And that makes a hell of a lot of a difference. So probably you've seen the Feynman rules. You have your propagators, you have vertices. This thing looks pretty much like a QED vertex would look like, with the difference that we have to account for the fact that there's color charges that change and that we have one of these generators there. Then we have a triple gauge coupling, and I just wrote plus cyclical, so you have Lorentz and color indices, and you rotate them through. You have a quadruple gauge coupling, and you have a coupling where gluon couples to 2 Faddeev-Popov ghosts if you have them. And these Faddeev-Popov ghosts never show up as external particles, so they only show up inside loop calculations. That's how that works. Did Kieran do anything like color algebra with you? Okay, then we just flick through it. So the structure constants F, A, B, C are defined through the commutator of the generators, and in fact, these are the generators of something that is called the fundamental representation, and these F, A, B, C are the generators of the adjoint representation. For those of you who like group theory, you will certainly know this. And yeah, the trace comes, if you trace it out, you get a delta function with a factor 1/2, and then there's this nice formula what happens when you have two two gluon indices, but 4 color indices. So this is an expression that comes when you have a gluon exchange between two quarks. Okay. Now let us first see what happens when we look at the self-energy diagram. So we have an incoming quark, say with color index L, emitting a gluon, having then a color index J, and J turns to I when the gluon is reabsorbed. And now we sum over A, and it turns out, after everything has happened, this factor here is proportional to CF, the Casimir operator in the fundamental representation, and delta function. And this CF is something that you can identify as the color charge of a quark. And yeah, it's 4/3 because n is for SU3 is 3, so you have n squared minus 1 is 8 divided by 2n, 6, 4/3. Okay, you can do a similar thing for gluon self-energy. So this is the gluon interacting with itself. So it's the gluon with the gluon loop. And similar logic, D comes in. You get two gluons with color index B and A. B and A get reabsorbed and make a C. What you get is Ca times delta Cd. So the self-energy doesn't change color, similar to the quark case. It doesn't change the color index. And this loop is proportional to Ca, which is 3. This is the color charge of a gluon. So what we see from that is that color charge of a quark 4/3, color charge of a gluon 3. Now we can look a little bit closer, and this is something that people quite often use. It's called the leading color. And the leading color is that you say, okay, n is a really big number, like infinity or 3. So we forget about, come on, it's the same for physicists, pretty much. So we forget about this nasty factor minus 1 because it's really annoying. And then what we see is that in this limit, the color charge of a quark is half as big as the color charge of a gluon. So color charge of a quark would be n halves, right? Color charge of a gluon would be n. And it recognizes the fact that gluons carry two colors, a color and an anticolor. Okay. And it's only 8 because, very simply put, if you put colors and anticolors together, you have 3 times 3, 9 combinations. But we have only 8 gluons. So which one is the one that is missing? It's the one that looks like blue anti-blue plus red anti-red plus green anti-green. And this doesn't count because it's just the one. So it doesn't have any color. And then it would be like QED. And that's boring because you already know QED. That's why there's only 8 gluons and not 9. But if you forget about this little glitch, in that specific case, quarks have half as much color as gluons, exactly half as much, in this limit of n going to infinity. Okay, just for completeness, these are the Gell-Mann matrices, and you see 1, 2, 3 look like the Paulis in the first two in the box 1, 2. 4, 5, 6 look like the Paulis in the box of 1, 3, and then you have 2 others. Okay, now why is this important? It's important because when you now start looking at what happens with the coupling constant, you know, under renormalization, couplings, masses, everything becomes dependent on a scale parameter, which is testament to the fact that we at some point truncate the perturbative series. So at first order, we have 2 diagrams plus possibly a third one, which is the ghost loop. But if you put it together, if you put these 2 things together, you get something that is called the beta function of Qcd. And this beta function of Qcd tells you how the coupling constant alpha changes with the renormalization scale mu r. In fact, it changes logarithmically. Now, you can expand the beta function itself in powers of alpha due to the fact that you have couplings here. And the beta function of QCD is positive. It's 11/3 Ca minus 4/3 Tr, which is 1/2, NF number of flavors. Now, we have 6 quark flavors. So if you look at this, 6 quark flavors times a factor 1/2 makes it a 3. So the second term here is a 4. And the first term here is an 11. So this beta function is 11 minus 4. 7. Okay. And it's positive. Now, what this means is the following. It means that when you increase the scale, your coupling constant becomes smaller. In QED, it's the other way around, because in QED, you only have a term that has to do with the fermion loop. Yeah, so this is the bit that comes from the fermion loop, and this is the bit that comes from the gluon and ghost loop. Now, in QED, the coupling constant increases with increasing scale. In QCD, it decreases with increasing scale. And it has a consequence because, conversely, in QED, the coupling constant decreases with decreasing scale, while in QCD, it increases with decreasing scale. And that is pretty much the plot that you see here. It's a slightly oldish plot, but not much changes here, really. So it's a plot from the PDG, which shows you the evolution of the QCD coupling constant with scale. And what you see is, when you're at about 100 GeV, your coupling constant is of the order of 0.12. And if you go down to 1 GeV, your coupling constant starts exploding, is 1/2. And you can imagine that as you push it, this thing will go through the roof. And so here's the comparison with QED. Pretty much the same thing. This NF is 1 to many. Now we can rewrite at leading order the behavior of the coupling constant alpha s as a function of 1 over beta 0 blah blah blah, and then there's a log term mu r over lambda QCD. Lambda QCD is called the Landau pole of QCD. And if you fit it to data, it's of the order of 250 MeV, about a quarter of a proton mass. So what happens there is the following. If mu r becomes lambda QCD, you get a log of 1, which is 0. So you get 1 over 0, and alpha s goes through the roof. And what I said before is this connection between asymptotic freedom, which is what happens at large scales. You have a small coupling constant, so quarks and gluons interact less and less with each other, whereas at small scales they start interacting very much with each other, and they form bound states. And in old books, this is called asymptotic freedom, and this bit here is called infrared slavery. The quarks are not free anymore; they're shackled. And yeah, they sit at the rivers of Babylon and cry a little bit. Probably. Okay, so this is pretty much what happens in QCD. Now, let us see whether we can turn it into something that tells us how the physics works. And so what I try to explain to you in the next 40 minutes or so, or an hour, is what this actually implies for when we want to start calculating stuff. Because what we see is we have a coupling constant that becomes very big at small scales or long distances. So our external particles, incoming and outgoing particles, must be bound states. We don't know how to calculate with bound states really in a meaningful way, because the objects of QCD are quarks and gluons, not protons and pions. So we have to make a transition from protons, pions, and other bound states, where we have to use effective theories and a lot of hope, to map them onto quarks and gluons where we know how to calculate, and then to map it back. This program goes under the name of factorization, and I'm trying to explain to you what the physics behind it is. Okay, it's like an intuitive understanding what's happening, and it also gives you an idea of why QCD behaves the way it does, and it will kind of inform you what you can expect in collider experiments. So this next hour is supposed to sensitize you for how QCD behaves when you start smashing protons into each other. Okay, but let us start with something entertaining and sort of simple. Let's say you have an electrical charge. Think of an ion or so at rest. You have an electrical field, right? How does it behave? It goes like 1 over r squared, because it's Gauss's law. Now, if we kick this thing to the speed of light, or let's say we kick it first, just a little bit, then you have a moving charge, and you get magnetic field. Yes, guys, answer, and we stay friends, and maybe I buy you a beer, okay? Sorry?
Negotiate for non-alcoholic beverages?
Yeah, for you I would make an exception, because I'm big-hearted. Huh? Come on, you're worse than my kids. You give them a little bit and they ask immediately for more. Okay, so we established, we kick a charge, we get a magnetic field. Let's say we kick the charge really hard. What does the magnetic field look like? Any idea? Is it like the electrical field? It's circular, right? Okay. Now, if we kick the charge really hard to practically the speed of light, what happens with the fields? Is the electrical field still spherically symmetric? No, it gets kind of, squeezed, right? Magnetic field? Squeezed. Exactly. So you have an electrical charge with a pancake of fields, right? Okay. Now these fields, how are they kind of oriented? The electrical field is perpendicular to the axis of motion, right? Magnetic field perpendicular to the axis of motion. Exactly. It's perpendicular to the electrical field, right? So you can define something that is called the Poynting vector that you know from classical electrodynamics, which gives you the energy flux of the fields. Okay? Okay. This is, hey, we worked it out together. I think that is a success. You're much more responsive than the PhD students I usually teach. So that's good. But then I don't buy them beer and I don't bribe them. That's maybe bad. Okay, so now the leap of faith is the following, and this is physics of the 1920s, actually. If you have an E and an B field that are perpendicular to each other, it's absolutely no problem to identify two circular polarizations, and you can say my classical fields, I can approximate them by equivalent quanta. So instead of saying, oh, I have a classical E and a B field, I say, well, I have photons. And the trick now is to say, well, I take the energy flux of my E and B fields and equate it with the energy flux of the photons. Make sense? Okay. Now, with this leap of faith, we can start discussing the spectrum of the photons. So you get a charge factor Z, an alpha over, you always get alpha over pi. And the only question is it alpha Qd, alpha strong or electroweak, but it always comes with pi. Alpha comes with pi. Then you have the omega over omega, where omega is the energy of the photons. And you get a dB perp squared over B perp squared, where B perp is the impact parameter, the distance of the photons from the charge. So what you see here is You get less photons in increasing distance. You get less photons with increasing energy. So your photons want to be close by the charge with very little energy. That is the winning. That is the winner. Now I could Fourier transform the full shebang, and I forgot a square here. The B becomes a K, so instead of impact parameter, I have transverse momentum. And what it tells you is your photon spectrum diverges, so you get infinitely many photons at energy 0 or transverse momentum 0. Now we could apply this to an electron, and what we learned from this is that if we want to build a quantum mechanical state for a lepton, it's very hard to define, right? Because this lepton, as soon as it moves, and it will always move there will always be a frame where this thing moves. This electron will always come with classical fields that we can reinterpret as photons. So this electron will always come with photons, 1 photon or 2 or 3, infinitely many, unless we tell the electron that we ask for minimal energy or minimal transverse momentum. If we don't ask for minimal energy or minimal transverse momentum, we get infinitely many photons in our Fock state. And in fact, we get a superposition of infinitely many states with up to infinitely many photons. Okay. There's a catch to that. So let's assume you are an electron. You fly your way. You have your fields around you, and you invested a certain amount of energy in your fields. So you have photons that come off. These photons will have a finite lifetime, and we're going to estimate it later. So after a finite lifetime, your photon will have to go, the photon that you emitted will have to come back and give you your energy back. Yeah, so that's the meaning of a coherent sum. You have your quantum fluctuations, and these quantum fluctuations will recombine. I explain this to you in quite some detail because lots of the logic that I use is something that we're going to use later when we discuss what QCD actually does. It behaves remarkably similar, actually. Okay, now, so we did this in a very kind of rough way. Let us calculate. So you open Jackson electrodynamics, and somewhere, I think chapter 10 or 11, we discuss, Jackson electrodynamics discusses the photon radiation of a dipole. So you have, let's assume you have two charges, positive and negatively charged, that go in two directions, v and v prime with speed v. And you ask yourself, how strong is the electromagnetic field at a position n, independence on the energy? And what you get is something that is called the radiation function. So you have the photon polarization vector, you have the two velocities of your two charges, and you have n the direction of the photon. And this is something that I'm fairly certain someone derived it for you in electrodynamics. Now, what I want to say is I can rewrite this thing because I'm not doing classical electrodynamics. I do particles. So I like to write this with 4 vectors. So I will promote my velocities. I will promote my velocities to 4 momenta, and I will promote my direction to 4 momenta of the photon. And instead of having a radiation function that gives me the intensity of the electromagnetic field, I can now say, well, actually, it's the number of photons, as before. And what I find is some phase space factor on alpha over pi, polarization vector times something that looks exactly like this thing. It's like the relativistic generalization. This thing is quite often called the iconal. And in fact, this is something that you would see exactly the same in QCD. It's already there in classical electrodynamics. Okay, Could be an accident, right? Okay. Let's do this in quantum field theory. Just, to prove something. So repeat the same exercise in quantum field theory. We have a virtual photon, we let it decay into an electron-positron pair, and we ask the electron-positron pair to emit a photon. We have two diagrams. We put it nicely together. So these are the spinors of the two outgoing charges. This is the polarization vector of the outgoing photon. This capital gamma is this big vertex times polarization of the incoming boson. Then I have a propagator and a gamma mu, and similarly those two terms. Okay. Now the manipulation I'm going to do is the following. I write it here. Is this okay? And I'll speak loud and So I'm sure this moves somehow. Okay, like that. Okay. The manipulation I'm going to do is the following. Let's say we have a p slash gamma mu and a u of p. What I would like to use are the equations of motion. So I know that p slash u of p is 0. That's the equation of motion. So how do I deal with this? I can use the anti-commutator. So p slash gamma mu plus gamma mu p slash is the anti-commutator. But we already established this is a 0. So by adding a 0, I promote this term to an anti-commutator. Okay? You must have seen this before. Otherwise, I would probably consider ritual suicide now. With a sword. And this is nothing but 2 p mu u of p. And so I use exactly that. I use exactly that, and I say, well, in the limit where my photons are soft, I can forget about the terms k slash in the denominator because they're small, soft photon. And then I get exactly these terms. P mu divided by pk, and the pk comes because p plus k squared is p squared, which is 0 because you have on-shell masses particles, k squared, which is 0. So you have just the 2 p mu divided by 2 pk. That's the thing that we get. If we would play the game a little bit more precisely, we would have terms that have to do with the k slash. Because I forgot about the k slash gamma mu terms. And I could massage them into a form that they look like an interaction of a spin with a magnetic moment. And that is kind of cute, because what it tells you is the soft radiation, the classical radiation pattern, is independent of spin, and that's actually quite good, because spin is an invention of quantum physics. So it's very good that spin only comes when we start discussing the quantum level of this. And if we forget about quantum, we find classical radiation back. Okay? So we get these terms. Now, let me just point out this pk. If we play it a little bit better, and I go back to this one here, what you see is this 1 minus Vn is something that looks like 1 minus cosine theta. So this here looks like 1 minus cosine theta. Yeah? Now I can write 1 minus cosine theta times the energy of the photon. So it's omega times cosine theta. And I can write this cosine theta as a sine theta half. Yeah? 1 minus cosine theta is something like sine theta half. So I see this is something like the omega over omega. It's something like the omega over omega dk perp over k perp. It's exactly the same form as before. So we get the same form in 3 different ways. Very naively, with help of Jackson and a lot of looking up and refreshing on undergrad physics and by doing quantum field theory. So there must be some truth in it. Okay, now what does it help me? What it helps me is I can now do in a first step I can write Alterali Parisi equations for QED. So what I ask myself is, if I have this fantastic Fock state of an electron with photons around, what is actually the probability to find an electron in this cloud? And it's clear, at leading order, no emissions of photons. What I will have is the probability density of finding a photon with energy fraction x with respect to the original electron must be a delta function, because if I don't emit anything, I don't invest energy in photons. So at 0th order, the lepton I find in the cloud will have exactly the same energy as the nominal energy of this full object. And of course, at leading order, I won't find any photons. But now when I start to include emissions, the probabilities of finding leptons and photons change. And we know how they change because we know that with every emission, when we emit an omega into a photon, we can rescale this. So this omega translates into an energy fraction of the electron. So omega and x are just related with each other by the overall energy. So I can write this differential distribution of photons with the log of k perp squared as alpha pi d omega over omega, or alpha over pi dx over x. So what it tells me is that the number of photons changes with the logarithm of their transverse momentum in proportion to dx over x. It's double logarithmic. So let us write this in a nicer form. So the number of photons with the logarithm of k perp changes like alpha over 2 pi d xi over xi from x to 1. And we have the lepton, the electron, as source of photons. After each emission, the electron will have less energy. So if you wanted to produce a solution, you could do it stepwise by starting with the delta function and then starting to add emissions and building your photons in a way. And the two objects here are called the splitting functions. We'll come back to them later. But what it boils down to is that for the splitting function where a lepton stays a lepton after emitting a photon, in the limit where the emitted photon is soft, so where z, that's the energy fraction the lepton has after emission, so in that limit, you see that you get something that looks just like a 2 over omega or so. So this is just the same dx over x just written now in z, which is 1 minus x. Okay. Now, what is missing here is I could also include splittings of photons into leptons. Then there would be a term where the change of leptons is proportional to the leptons you already have plus photons that split into leptons. And we're going to see this in QCD. In QCD, we would also have a term where gluons are made from gluons. So QED is a little bit of funny. You have 3 splitting functions. In QCD, you have 4 splitting functions. And that makes it look much nicer. Okay. Are you with me till here? Yes, no, maybe? Okay. Let's do a little bit of quantum mechanics. What we'll try to do now is we'll try to estimate the lifetime of one of these fluctuations. I want to know how long they live. And we do it in 2 ways that are lead to the same result. Let us first assume it in the following way. Let's say our two objects, our electron and our photon, actually real objects, and we ask ourselves, how long does the intermediate state live that produced the electron and the photon? So in order to produce an electron and a photon, this thing must have a virtual mass. And in its rest frame, the lifetime of such a system with a virtual mass, right? The delta energy times delta time is a constant, so we know that the lifetime delta time scales like 1 over delta energy, and the only thing that you have that has the physical dimensions of an energy is the virtual mass. So the lifetime of this virtual thing, its own rest frame, is 1 over its mass. Let's forget about h bars, and it's, you know, we just estimate, it's uncertainty relation. But this thing is boosted. So we get a boost factor, and the boost factor is energy over mass. And if you put it together, you get energy over virtual mass squared, so energy over p plus k squared. Now we put it all together, and we find that this virtual object has a lifetime that scales like energy of the photon divided by its transverse momentum squared. So in other words, if I want something with a longer lifetime, the photon will have to have more energy and less transverse momentum. So the less transverse momentum you have as a virtual photon, the longer you live. If you stray too far away from your lepton, you're pushed back very quickly. You know the things, there's something that exists in the UK, and I always found it very interesting. I wish we would use it for our kids. You give them some harness, and you have like a rope. You've seen that before, right? To make sure that kids don't do silly stuff. It would be great to have some kind of like a little engine that instead of you pushing, you press a button, it goes, and the kid goes, bah! So think of the photon as a kid. If the kid runs away too fast, I press the button very quickly because I get really, really antsy. This kid is up to no good. Press the button, bam. Lifetime of the child-parent excitation, very small. Okay? That is pretty much how it works. The kid walks next to me, I don't have to press the button. Yeah? They will have to recombine. So, the way I did it was, I discussed the lifetime of the source. I could turn it around and make the virtual mass this electron has to have in order to make sure that this thing is on shell. Yeah? And let us say this thing here is on shell. Yeah, and let me distribute the virtual mass between those two. Then they go back to back and they have to recombine. Because our electron, if you leave it alone, is not supposed to decay. It's an on-shell particle, it has lifetime infinity, so all these quantum fluctuations have no real life. They have a finite quantum mechanical lifetime, yeah, but it's very finite. It has to be, because otherwise this thing would decay. I could make the same argument, and this is pretty much the second way to introduce it. I put the virtual mass on the photon, I come up with exactly the same result. I just want to show both ways, because it's the same kind of thinking. Yeah?
The way you were phrasing it earlier sounded like you were saying that the photon moved away, there was some sort of attractive force pulling it back, and not like a lifetime it would stop existing. Is it actually that the photon, the virtual photon is experiencing some sort of attractive force, or is it just like you're not going to find them farther away?
You don't find them because they just have enough time to go far away.
Okay.
Yeah. So what you see here is something that is, this is the effect of quantum currents. You have a coherent state, your incoming, your stable electron flying on a straight line, but then you have this wobbly stuff going on, and you have to kind of account for the wobbly stuff. And so you have you have quantum fluctuations, and you have to ask yourself, how long do they live? So they do not have to respect. Well, they kind of respect form momentum conservation in such a way that the intermediate states, in a very bizarre way, are off-shell. You can't look at them because they have a finite lifetime and it's a coherent state, right? So looking at them is a little bit of a logical fallacy. But I need to do that because I want to introduce factorization, and then I need the lifetime argument again. The logic is the following. So you have your coherent state, and unless you have an interaction that happens on much shorter time scales than my lifetime, and then I don't see these quantum fluctuations. So in order to see my fluctuation, I must probe them at scales that are higher or at lifetimes that are shorter. It's like the law of microscopy. If you want to do something in time-resolved microscopy, your photo apparatus must be fast enough to take the pictures. If you can't take the pictures, you don't see any kind of action.
Yeah.
That's pretty much the logic. Now, I introduced these lifetime arguments because with this omega over k perp squared, I will come back to that later. Okay, you basically forced my hand to explain what factorization is, but that is pretty much the idea. And it means that if we start probing our system at energies at scales that are sufficiently high, at times that are sufficiently short, then we can pretend that the particles we see in the quantum fluctuations behave as if they were free, with an energy, with a momentum. So this extra interaction would force them on their mass shell, because then you start borrowing energy from an outside source. And all your off-shell particles can go on-shell and have real life instead of just virtual life. Yeah?
Can we visualize this process using Feynman diagrams? It
No.
looks like it's E goes to E 403 means like it's like self-energy correction.
It is, yeah.
But it's not that one.
No, it is in a way it is a self-energy correction, because these guys have to recombine. But in a Feynman diagram, you would not discuss lifetimes, really. And
So that means we cannot visualize it using Feynman diagrams?
no, I wouldn't know how to do that really. Well, I'm used to do Feynman diagrams. The problem here is the following: we are used to do Feynman diagrams in momentum space. So the notion of space-time doesn't exist really. And for that to work, what you would have to do is you would have to kind of cut your Feynman diagram and start forcing particles on their mass shell, which kind of defies the purpose because you want to have the coherence. So I'm not quite sure how you would do that. Okay. Let me go back to this running of alpha S. So until now it was fun because it was electrodynamics, where the coupling constant is finite and doesn't increase. Now, if we would do the same thing in QCD, you would see that if we start probing k perp scales that are smaller and smaller, you would have stronger and stronger coupling constants. So that will kind of blur the picture a little bit. Now, the one thing I want to say is the following here. I can use exactly the same argument that I did before, and I can ask myself, so I have a quark or a gluon running on a straight line. If I only consider one emission, what is the spectrum of this one emission? And the spectrum of this one emission would be the color charge, alpha S over pi, the omega over omega, dk perp squared over k perp squared. And in a single emission picture, my number of emitted gluons would behave like this thing. Yeah? So pretty much exactly the same. The only difference is, instead of an electron which has quantum fluctuations, we now want to discuss a bound state of quarks and gluons. and ask ourselves what happens. And what would happen is the following. At some scale, your proton would consist of a number of quarks and gluons. These quarks and gluons start emitting further gluons, and similar to what we saw in QED, they would recombine. Right? So instead of one electron emitting and reabsorbing photons, you would now have 3 valence quarks or whatever emitting and reabsorbing gluons, and in addition interacting between each other because they're bound states. So the picture is much more complicated, but the logic is the same. Our virtual excitations have a finite lifetime. They will recombine. Now, this is pretty much what it is, right? Let's assume you have, say, a meson. Yeah, these guys interact with each other because ultimately they glue together, but they also emit gluons and reabsorb them. And sometimes the gluons split into quarks. The quarks go together again. You see, it's like it's like a little kind of, it's like pond life. Pretty much everything goes through each other. Now, what happens when we have a hard interaction is the following. Let's assume we now have an interaction of, say, a photon that has enough momentum to resolve the very short time scale of this fluctuation. So it would see one of the quarks, but because it has enough energy, it would start donating 4 momentum to the quark-antiquark, and out of a sudden this thing here doesn't have a virtual mass anymore. It becomes real. So it gets kicked out of this coherence picture, of this coherent emission and reabsorption. It gets kicked out. But because it gets kicked out, the other quark doesn't know what to do. It doesn't have a partner, right? It wanted to kind of combine with the quark, but it can't because the other quark is gone. And that is really bad because then this gluon here doesn't know how to recombine. So all your coherent emission and reabsorption pattern completely unravels. So you kick the thing, and out of a sudden, the poor quarks and gluons can't recombine anymore. The cord has been snipped. This is what happens with kids when they grow up. They get enough energy and okay. Now we can argue whether we look forward to that or not. So what happens is the following. The coherent picture is broken by a hard interaction, and the hadron does not recombine anymore. It disintegrates, and depending on how much energy you pump into the system, you get more and more hadrons out of it. It's one way of looking at it. Another way of looking at it is to say, well, actually, this is initial state radiation. So we see the quark, but before we saw the quark, on the way it emitted lots of gluons. It's 2 different ways of looking at it. Now, let us see how we can make more sense of this in a more quantitative way. And for that, I want to discuss something called deep inelastic scattering, which is pretty much a process where a photon with a high virtuality hits a proton. So you have a photon that has a large virtual mass Q that is much larger than the proton mass. So this guarantees that the virtuality of the photon, which acts as a probe, resolves scales that are much smaller than the proton radius. So this photon will not see the proton as an integral object. It will start probing the inner structure. If it would probe just the full proton, naively it would just see an object with charge 1. If you look a little bit closer, it would see that the proton has some magnetic moment, etc., and maybe form factor. But if we start hitting the proton really hard with a photon that has a sufficiently large mass, we probe a small area in the proton. And I'm going to use a very bizarre frame. It's called the Bright frame. And it's a frame where the photon doesn't have any energy and only momentum. And because I'm lazy, I put it into Z direction. And in that frame, it interacts with a quark that just gets bounced back. Yeah, so this is a frame where the photon comes from, say, the left, a quark comes from the right, hits like a brick wall of the photon and bounces back. And yeah, I introduced this Purkane variable xp, which is yeah, momenta in z direction. You can see that. Now, let us play the game. The interaction time between the photon and the proton, the interaction time must scale like 1 over the mass of the photon. And we said, well, the mass is now completely in our frame along the z-axis, so it's like 1 over the photon momentum in z direction qz. Now, when you do microscopy, you have to make sure that you see what you see. And that means the photon wavelength must be smaller than the quark wavelength. So otherwise, the photon wouldn't see the quark, right? But at the same time, for the quark to see the photon, the quark wavelength must be smaller than the photon wavelength. That's a little bit diabolical, because the only way to achieve this is by saying that the two momenta are identical. So you basically have to convince yourself that the only quarks the photon can see are the ones which in the bright frame have the right momentum to be seen and to see the photon in return. Because you can either think of the photon probing the proton, or you can think of the quarks in the proton probing the photon. So it must be symmetrical. Now, because of that, you remember we had the lifetime of the parton. And we said the lifetime of the parton is like energy or momentum along the z-axis over transverse momentum. And in order to see stuff, the lifetime of the parton must be longer than the interaction time. So pretty much, the parton must live before it interacts, because if it doesn't live, it can't die. Pretty much, that's what it boils down to. So lifetime of the parton must be larger than the interaction time, and that means the longitudinal momentum must be larger than the transverse momentum. Otherwise, this interaction cannot happen. And if it's sufficiently much larger, then you can treat your partons in the proton as quasi-free particles that move pretty much in parallel to the proton. Because the transverse momentum must be small, right? If you use this logic, you use something that is called the Collinear Factorization. And it will allow you to decompose the description of your hard process into two parts. There will be a hard process where the photon interacts with the quark, and there will be a part where the quark is taken out of the proton. So that's an independent proton-parton transition, and it's called factorized because it says that you can treat them independently from each other. For this to hold, the interaction time must be significantly smaller than the formation time. So the transverse momentum must be sufficiently smaller than the longitudinal momentum. Naively, that means the partons move parallel to the proton with practically zero momentum. And in that case, we can say the cross-section is proportional to the quark charge squared and to the probability of finding quarks inside the proton. And these objects here are called parton distribution functions, and well, we're going to discuss them next. Okay, so there is something there that you have to be aware of. The very moment you start using perturbative QCD, you have to make sure that you can discuss quarks and gluons. So you have to abstract away the proton, and the framework to do that, there's different frameworks to do that. The most used one goes under the name of collinear factorization. There's one or two other factorization schemes which are a little bit more bizarre. In collinear factorization, you treat the proton, practically speaking, as a bag of partons that fly in parallel and are quasi-free because you probe them at a scale that is large enough that bound state effects are really small. Or in other words, that the lifetime of your fluctuations is so big that you don't, that recombination effects don't matter. That is the heart of the factorization theorem. The problem is it has been proven for only two processes, DIS and Trillian production. So everything else is much more complicated. It's not clear whether you can prove it really, but we still use it because it works. So it's a very physics way of doing stuff. We can't prove it, but it works, so hey, let's use it. So collinear factorization, the very moment you sign up to it, you buy something. You buy that you have to use PDFs. The advantage is they're universal and process independent because you factorize them. And you buy into the fact that your partons fly collinearly to the proton. Sure?
Does that mean that collinear factorization needs the leading order in
Exactly. So if you think about that the p-perp of your incoming partons is important, you have to do something else. I'm not discussing the partons that come out of the process, but the one parton from each beam that goes into the process doesn't have any transverse momentum. So if you are sensitive to transverse momentum, you discuss something that goes under the name of higher twist. And that is process dependent in this scheme. Yeah? That's the kind of, for everything you do, you pay a price. Yeah? Okay. Now, we can say we have quark and gluon PDFs, and we can now discuss how they scale, how they behave under scale changes. And similar to what we had before, we now get a matrix of splitting functions. So it's an integral differential equation, right? You have a differential equation, differential kernel to the left and integral kernel to the right. What it basically tells you is the following. If you want to know how many quarks or gluons you have at energy fraction x, this depends on the number of quarks or gluons at an energy fraction z that is larger than x, who then emit something. What you realize is, in the case of QED, we had a solution at leading order. For QCD, there's no solution at leading order because perturbative QCD is incapable of describing a bound state. So if you want to know what the parton distributions are, you have to work, and I'll very briefly sketch what you have to do. But you have to realize these objects here are non-perturbative objects that we take out from data. There's no first principles calculation that gives it to us. Maybe a couple of years, dozens of years down the line, lattice QCD will do it, but at the moment we have absolutely no handle on these objects from first principles. We have to measure. Okay, just for completeness, the splitting functions. We're going to calculate in a very rough way this one in a later lecture. And for those of, do you guys want to calculate stuff when you go home or in the afternoons? Yes? No? Huh? Do you want to calculate stuff in the afternoons when you're bored and drink your mate tea or so? I can calculate while drinking. Actually, my strongest suit is supervising others calculating while I drink. I'm really good at that. So no, I mean seriously, if you feel that you want to calculate stuff, we can send me an email or so, let me know. I have a couple of sort of worked out problems. One of them is how to calculate a splitting function, for example. So for those of you who want to know a little bit better, it's kind of interesting because ultimately you only know stuff that you calculated. So what I do here is I don't let you calculate, I give you the ideas and you have to decide whether it's interesting or not. And if it's interesting enough and you want to know, you have to calculate. I don't believe in Platonic physics. You know, you have to touch stuff. You have to get dirty and calculate. It's sad but true. Okay, so what do these Parton distributions look like? In a very naive picture, let us do something very naive. Let us say we have a proton that consists of 3 quarks, and let us pretend there's absolutely no interactions. There's some magic that bounds them together, a plastic bag. But so they're in this plastic bag. They don't know what they do. So what would their typical energy be? You have 3 quarks. Every one of them will have a third of the energy. Why? Because you don't want to discriminate. Protons are equal opportunity employers for quarks. So your 2 U quarks and your D quark will all have the same energy, 1/3. Now you switch on interactions. Now let us do it in a very nice way. Let us say we have these 3 quarks and they're kind of bound together with springs. So you have 3 springs and 3 quarks and they go and they wobble. Some of them may wobble a little bit more than the others. So what will happen is, if you have these rubber bands or springs, the average energy of your quarks will kind of diffuse a little bit, depending on how much your rubber band allows you to wobble. But now if we switch on interactions, we know how they behave. These interactions behave like the omega over omega. So we want to have lots and lots and lots of partons with very little energy. And that's why our Parton distribution function will typically become larger when the energy fraction becomes smaller. They scale like 1 over x to some power. Okay? Now, gluons just scale like that. Quarks, the ones that were the original 3 quarks in the proton, they kind of remember that they had a special role. That's why there's this little hump. They will have lost some energy because they will have emitted stuff, right? So they will not have their 1/3 energy anymore. Typically, the energy of the valence quarks is at about 0.1, 0.15. So about half to 2/3 of the energy is radiated away into gluons. But in Parton distribution functions for U and D quarks, you see this hump. And that is the valence, the memory of valence quarks. And that's kind of interesting because it tells you the process where you can suck the most energy out of the protons are processes where you have 2 valence quarks colliding. And very naively, because they peak at about 0.15, you know that the typical energy range would be 0.15 of the center of mass energy of the LHC. So about 2 to 3 TeV is something that you can reach without any problem if you collide 2 valence quarks. That's why weak boson fusion works pretty good for trying to produce relatively large mass systems, because you have, with the valence quarks, you have a lot of oomph in the system. On the other hand, if you have something that is relatively light, think of the Higgs boson, then the sheer fact that you produced gluons like mad will help you, because you sit now at a place where the PDFs are really big. That's why for LHC it was actually a good idea to increase the energy, because the more you increase the energy, the more the energy the gluons need to produce a Higgs boson becomes smaller, and it scales faster than linearly. That's why you gain a lot by increasing the energy. You gain more than you would assume with linear scaling. And that's completely in the PDF. So if you understand how these PDFs behave, you can kind of design the process that you want, the kind of process with which you can test your mass range. Okay. Now, there's another thing that PDFs have to satisfy. The first thing they have to satisfy is if you sum over all partons at a given scale, the sum of all the energies must be the energy of the proton. Okay? What it says is basically you can't lose energy. The constituents of something must have the same energy as the something. Otherwise, they're not, you miss the constituent. So if you sum over all constituents, well, you have to get a 1, the original energy scaled. You also know that a proton has as flavor quantum numbers UUD, 2 U's, 1 D. So U minus anti-U must be 2, D minus anti-D must be 1, strange minus anti-strange, char minus anti-char, bottom minus anti-bottom, top minus anti-top must be 0. For gluons, we don't know. There's no flavor to them. They're just color. Okay? So when you have PDFs and you want to make a model of PDFs, you have to make damn sure that your model kind of incorporates these sum rules, because otherwise you do not describe a system that is a proton, you describe something else. If you violate the momentum sum rule, honestly, you look a little bit like a dodo, so it's not good. Flavor sum rules are a little bit more subtle. If you violate them, people will typically not necessarily notice. So you may get away with it, but it's still not good. Because deep in your heart you know. So a couple of years ago, practically before you were born, people discussed a special kind of PDF specifically for Parton-Shaw Monte Carlos. And in the beginning, this sounded like an absolutely spiffing idea. It turned out that these PDFs did not satisfy the momentum sum rule. And when it dawned on people that there was a little problem, they were faster forgotten than they were produced. So they had an imaginary lifetime. Okay, now here's one of these things that I have the feeling you have to show in every QCD talk. This is the combined PDF fit. So what they measure is a cross section. It's basically the sum of all PDFs for different values of x in dependence on q squared. And what you see is the following. These lines are not necessarily constant. So what you see is that the PDFs change with q squared. That goes under the name of scaling violation. It's a memory of the fact that your partons emit partons. If the partons would not emit partons, these guys would be flat. Okay? Now, what does a proton look like? So let us think about what a proton looks like. And we go now into a funny space. We go into space where to the top we make the scale larger and larger. So we probe the proton at smaller and smaller distances. And when we go to the right, we probe constituents that have less and less energy. Okay, so down here, low scale, low energy, 3 valence quarks. If at low scales you want to see what happens at smaller and smaller energies, your proton becomes at some point really empty because all the momentum sits in the valence quarks. Makes sense? Now, if you stay at relatively low energies of your partons and you increase the scale, you still have only 3 valence quarks. You may have a few less because they may have radiated, but it stays where it is. It only becomes interesting when you go to larger scales and smaller energies, because then the proton starts filling. You start seeing more and more and more and more partons. And at some point you see so many partons that you can't see the proton anymore for all the partons. Or if you phrase it like this, these guys start overlapping. It's called the black disk limit. It basically means that the cross-section cannot become bigger than the cross-section for induction cannot become bigger than the equivalent area. And if it becomes bigger, you have a problem, and then these guys have to recombine. And this is something that is beyond Alterali Parisi. Every now and then people claim they've seen something like that in deep inelastic scattering, but most of the time it's BS. And they just didn't do it very well. Heavy ion people find this very interesting because in heavy ions you see how the nucleons get all squashed on top of each other because the nucleus is like a pancake and you squash nucleons into each other. So it's much easier for you to overfill the area. So in nucleus-nucleus collisions, the assumption is that you see much more of this. Okay, can I have 2 more minutes and then okay, because then we finish this PDF thing and never talk about it again. So just as a reminder, these guys are essentially non-perturbative because if you wanted to know the answer, you would have to be able to answer the question how many partons are in a nucleon based on first principles. Before you can't do that, they're non-perturbative, and you have to find a way to measure them. So what people do is they measure a lot of different processes at different scales and different energies, and they try to fit the PDFs based on the cross sections they see. And then use the Alterali Parisi equation to move it around. So the logic is you measure at scales, and then use the Alterali Parisi equation to put it all down to a level of, say, of the order of 2 GeV, where you have some fitting functions that may or may not be complicated with parameters, and you try to fit the parameters in such a way that when you evolve back with Alterali Parisi, you find the right cross-section. So what people used were deep inelastic scattering experiments, electron-proton or electron-nucleus, some of them really old. Some of these experiments sound like artificial colors. It's not healthy. So deep inelastic scattering. Then there was a batch of experiments where you do where you do trillion type of production. So you collide two nucleons and you look for lepton pairs. The latest batch before LHC was done in blue at the tevatron, and then you have the tevatron where they typically look for jets or again for gauge boson production. And what you get then is, I think I have to show the CTEC PDFs, otherwise my co-author Joey would probably lynch me. At 2 GeV, see the up quark, that's the valence, the down has a valence, and you see how the anti-up and the up become very similar, and the anti-down and down become very similar, and strange bar are identical. And the gluon, well, is divided by a factor of 5 because you have lots and lots of gluons in the game. So you go to small energies and you get shed loads. Now if you go from 2 GeV to 100 GeV, you see what happens. All your sea, like ocean, your ocean of partons becomes a really big ocean. The valence hump starts disappearing because you now have a lot of phase space to emit like mad. And you see how the ocean goes through the roof. That's why when you start probing relatively low mass processes, you typically see the sea. And when you start probing higher and higher mass, you only see the valence surviving. Okay? And that is something that that is one of the things that you should understand if you want to do LHC physics. In order to produce something, you have to know which partons are available for you. Otherwise, you can't produce it. So if you have a process that completely depends on gluons in the initial state, and you want to probe, say, something like 5 TeV, not going to happen, mate. On the other hand, if you're interested in something like 150 GeV, you have a really good chance. So that's the game. Okay. I stop it here and we continue tomorrow with hadrons in the final state. I don't know what the form is. Are you supposed to ask questions now, or is this now just a relief? Yeah. 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 Here, of course, you would see charm. We would see charm and bottom, but then it becomes so crowded that you don't see anymore. Yeah, sure. Because look, at the moment you see up, down, and up bar, down bar, gluon, and strange bar. You would have charm and bottom, and of course you could ask yourself. So if I was then Brodsky, I would now tell you, of course, there's intrinsic charm in the proton. So charm and anti-charm are not the same. I don't show you the plot for a reason. But you have a lot. You have more curves, yeah. Absolutely. So at some point you have to ask yourself whether there's a top in the proton. And I mean, that's an interesting question, because then you have a mass, you have an object that itself has a very short lifetime. The lifetime of the top is really short. So you have to ask yourself, how do you probe this thing? So charm and bottom is kind of fun, and we all agree this is not a problem. With top, I think maybe one has to think a little bit better, or go to really so high energies that no one cares anymore, and the top is treated as massless.
Bar closer together or the same?
Not in CT14 next to leading order. That's what comes out of the fit.
Well, what is it?
I have absolutely no idea. I don't know. I think you're onto something, because naively I would have thought they should look the same. But it's one of these things. So for a long time, when people did the fit of the function, they assumed up and down bar to be the same. And recently people introduced what they call isospin violation, which is the splitting of the two. Apparently, there's data that support that. I find it surprising. But I mean, you can't really argue with data. So, yep.
So you come up with these PDFs by doing a bunch of experiments and comparing that and extrapolating and whatnot.
Yep.
But most of the experiments are relatively low energy. They're more precision experiments. So one of the arguments I've heard against the 100 TeV collider is that we don't have PDFs for that energy that are accurate enough for us to actually get any meaningful information from anything that happens.
I'm not sure. I'm not sure, because I think we understand the Alterali Parisi equation extremely well. And the higher the scale we go, the better it becomes, because the coupling constant becomes smaller. So this thing becomes rather more stable than more unstable. Now, it is there's some truth in the statement, and that is when you're interested in relatively low mass objects. So if you want to probe something with a mass of, say, 10 GeV at 100 collider, at 100 TeV collider, you sit at 10 to the minus 4, 10 to the minus 5, and that is where the PDFs become indeed unstable, because we lack support, we lack the measurement. Let me go back to where we have the measurements. So what you see is when we go below 10 to the minus 3, the measurements become kind of fewer, and some of these dots are really awkward ones. Yeah, funny names of experiments, artificial colors. So we lose the quality of the data. However, I would not build a 100 TeV machine to check for 10 GeV. Yeah, so I just for the sake of the argument turned around. If you ask me why would you be interested in a 100 TeV machine, and I actually am. I want to probe 10 to 20 TeV, and that is this region here, abundance of data. And we understand the PDFs there really well, with an error of the order of 5 to 5%, maybe less. So we can do measurements like searches for high mass new states. You want to go to low mass? Okay, different game. Yeah, so your statement is at the same time right and wrong. It's right because we lose at the low scales, but honestly, someone who tells me they want to build a 100 TeV collider to do B physics, well, strangulation. It comes to mind. No, you have to do something with this. I mean, it's so stupid. You don't want to do that, right? I mean, we want to see new stuff, not B's. I know B's. Okay, there was another question somewhere. You. Yeah. No. So at the moment we have of the order of 6 different PDF sets, 3 that I would call mainstream and 3 that are not so mainstream. So the mainstream ones are MMHT, which in the past was MSTW, which in the past was MRST. And they come with names like MRST06, MSTW08, and this 08 or 14 gives you the year when the fit was done. So CT14 is a group that goes under the name of CT or CTEC, and the fit was done in 2014. That's CT14. The NNLO tells you the accuracy of the processes and of the Alterali Parisi evolution in it, okay? You could do the same fit at next to leading order with doing your calculation at next to leading order accuracy and doing your Alterali Parisi evolution at next to leading order accuracy. Okay? So everything that is CT tralala, blah 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 LO, is the same group of people doing fits at different times, at different precision. That's the 2 tralalas with increasing data. So it's clear, say the CTEC 6 data or so, were pre-LHC, so no green dots. Okay? So we have CTEC or CT, MMHT, which changed its name, and NNPDF. The difference is a little bit in how they assign errors. There's a little bit of a difference in their selection of data. And there's a difference in how they arrive at the functions they fit at the low scale. There's different prejudices that come into play, and it has to do with how many terms do you put into a parametric expansion. Okay, so there's slight differences, but these 3 mainstreams, because they have relatively similar data sets, relatively similar way of doing the stuff, come out with relatively similar results, and the relative discrepancy over a wide range of what I would call relevant scales is of the order of 5–10%. Okay, and then you have the outliers. There's something called the Hera Pdf, and you will have guessed it. This relies only on Hera data. So it's only some of the red points here. There's ABM, and I don't want to talk about them. And there's GRV, which have another prejudice of how they do stuff with their function and in their selection of data. Okay? I'm told we should stop. We can do it over dinner or so, or mate tea or beer or whatever. Okay?